Hello, class. I thought that we would talk a little bit about vectors today. Uh, we're going to get into things that use vectors and use operations. We'll be working with vectors and vector fields and everything like that. So, um, we've got to understand the basic operations of vector arithmetic and everything like that. So that's what I wanted to start off with today. We've got other things I can talk about along the way, but really what we want to do is review vectors. And so if you're all set with dot product, cross product, what they are, how to figure those out, you probably don't have to pay as much attention to this uh, lecture, except at the end of the lecture, I'm going to show how I would use this if I had, let's say, a vector field dotted to a line integral moving through that vector field, right? Similar to a rocket that is taking off from Cape Canaveral and is going against the force of gravity to get up to an altitude of 200 or 300 miles, right? If I was to do a integral through that, what would I get? Anyway, like I said, that's something for later. That's not what we're working on in the beginning. In the beginning, we're working on just what the heck is a vector and how do I put, vector arithmetic together for those people that may not have had me for engineering mechanics. I'm going to write down a couple vectors and we're going to do some vector operations because vectors are just so easy to work with. And if you haven't worked a lot with vectors and the engineering notation for vectors, then yes, pay attention as much as you possibly can. And I'm not sure how you got by me because I think I have been about the only person teaching this for, well, I think it's only been like 2 years. So some of you, if you're on the decelerated program, you may have not had me for engineering mechanics. You may have had somebody else for engineering mechanics, but whatever. Okay, so these are two vectors, and these are vectors in the standard notation. I is a unit vector along the x direction, j is a unit vector along the y direction, k is a unit vector along the z direction. And I've got two different vectors. Don't worry about what they represent right now. Could they represent acceleration? Sure. Could they represent force? Sure. Could they represent electric fields? Sure. All of those, right? However, they don't have to, and they could represent any of those vectors, right? As long as it's a vector that we're representing. You can see the little arrow over the top. That's also the engineering notation. So if I was looking at adding those two vectors together to come up with another vector, a vector c, what would I get? Well, I get 3 minus 2. That gives me 1. In fact, I'll put a 1 there, but usually with the 1, you just not even write it down. And then 3 plus 4, so that's 7 j hat. And then 5 minus 1 is going to be plus 4 k hat, right? So that's adding the two vectors together. What if I wanted to get the magnitude of A? And also at the same time, like I say, if you haven't had me for engineering mechanics, look at the notation, understand the notation. I'm using absolute value signs around the vector symbol for A, and that means magnitude. What is the magnitude of A? And how do I find the magnitude of A? Well, I use Pythagoras' theorem, where I just square the individual. Pythagoras' theorem, by the way, doesn't just work for 2 dimensions. You may have thought of Pythagoras' theorem only applies to a 2-dimensional right triangle. Well, it doesn't. It applies to higher order perpendicular spaces as well. So it works just as well in the third dimension. So the magnitude is just going to be the square root. I was thinking whether should write it out or not, but the square root of the square of 3 plus the square of 4 plus the square of 5, all taken to the square root, because that's Pythagoras' theorem. I'll refer you back to that, but I'm sure that everybody is aware of Pythagoras' theorem, and that comes out to 7.07. Now, if I look at the magnitude of B, and you might say, hey, he's going a little fast here. And that's only for people that haven't had me for engineering mechanics before, because for the people who have had me, you already know this, and you're probably bored to death, and you've probably already shifted to the end of the lecture just to see if I've done anything that's really remarkable, and I may not have, except for that line integral stuff at the end. All right, and so B then, the magnitude of B, doing the same thing I did there, is just going to be -2, right? So if I have -2 squared, isn't that the same as +2? That's right. So -2 plus 2, it doesn't matter. And then I've got -1 here squared as well, so that's just going to give me 1. And so if I take the square root of all of that, I get 3.74. Now, if you look at these two, you'll see that they're almost 90 degrees apart, right? And yes, I'm going to draw this Cartesian coordinate system over here. I'm going to draw it like this. I'm going to make that my y-axis. And then I'm going to make my z-axis over in this direction, and then coming out of the board. Oh, I didn't draw that too well, did I? Good thing I draw it. There we go. That's not so bad. Out of the board then, and in this direction over here would be my x-axis, right? Because y, x, and then z coming out. It's still exactly orthogonal. That's the plus z, that's the plus y, that's the plus x. You know, I'm sure that being engineers, you can manipulate that in your head, or at least 73.4% of you can manipulate that in your head to see that that's exactly right. Now, the reason that I did that, and of course I'm just going to draw the minus z-axis in here too. The reason I did that is, let's plot these, right? So let's see. I've got 3 in the x direction. So let's say I come down here, that's about 3 in the x direction, and then 4 in the j direction would bring me up to about here, and then 5 in the z direction. So that would be going in that direction. Does everybody see that coming out of there? It's pretty much in that direction. 3 over here, then 4, and then 5 out there. So it's really coming straight out of the thing. And then if I go -2, that would be back here, and then +3, and then minus k would be about here, and then that would be drawn in that direction. So I can't really show it all that well, but it is. Let me tap that. That should be coming in better. There you go. That's right. Refocus yourself. So you can see that we've got an angle between there. We don't know what that angle is because we're trying to look at a 2-dimensional angle in a 3-dimensional framework that we have here. And we can't really see that. But whatever it is, we can run a plane through there. If I have 2 different vectors, right, that are connected at one end, there's no way that I can twist. There's no way that I can twist those vectors that Well, there's everywhere I can't twist. There's no way that I could twist those two vectors attached to the end that I couldn't put a plane right through those two vectors. See, no matter how I twist them, if I twist it this way, I can always put a plane through. I can always put a plane through those two vectors and find the smallest angle between the two. The smallest angle. So what would that be? And of course, the smallest angle I'm talking about here is like that. You can't really see it in 3 dimensions, but I can. Looking at it from here, it looks much more 3-dimensional. So anyway, we're going to find out what that angle is because we're going to define the dot product. The dot product, A dotted with B. And now what is A dotted with B? I'm going to define the dot product right here. It's the magnitude of A times the magnitude of B times the cosine of the angle between the two. That's the definition of the dot product. And so I want to look at some of these, dot products to begin with. So how about I hat dotted with I hat? And remember what I'm saying, I is a unit vector. It's a vector that's got a number 1 meter per second, 1 Newton, 1, God, I'm trying to, meters per second squared. I'm trying to think of vector quantities, of course. But it's always 1, and it's 1 in the x direction. So we know that the magnitude of a unit vector is 1, right? And then if they're both going in the same direction, 1 in that, and then 1 in that direction, well, they're both going 1 in the x direction. They're parallel to one another, right? So it'd be the cosine of 0 degrees. And we know the cosine of 0 degrees, that's 1. So 1 times 1 times 1 equals 1. That's pretty good. The same thing would be true if I had J dotted with J. So J dotted with J. Now, did I say it was 1I? I did not. This 1 that you get here is a scalar. It's a number. It's like speed as compared to velocity. Velocity is something that has magnitude and direction, but speed only has magnitude. So what we've got here is a scalar. So when I dot multiply 2 different vectors together, whether it's the unit vector here or these vectors up here, I'm always going to get a scalar. When I look at the magnitude that I've got up here, that's a scalar, isn't it? Because that gives me the magnitude of, it doesn't give me, it's not a vector because it doesn't include direction, does it? So it's just a scalar. J dotted with J, 2 vectors dotted together, they give me a scalar. And of course that would be 1, and K hat dotted with K hat, that would be 1 too, right? Now all of those make sense. But what if I did I hat dotted with J hat? Well, let's see, that would be the x direction dotted with the y direction. X dotted with y, right? Well, that's 1. It's a unit vector, so 1 times 1 times the cosine of 90 degrees. 1 times 1 times the cosine of 90 degrees. Oh my God! That's 0. So anything dotted outside of itself equals a 0, and everything dotted with itself equals a 1. There's COVID. So let's dot the 2 together. Let's do that. Let's dot A with B. A dotted with B. I hope I'm recording. Is going to be 3 times minus 2. So that gives me minus 6, and then plus 4 times 3, which is 12, plus 5 times minus 1, which is, give me that thing, which is minus 5, right? Oh, I did it again. Oh my God. All right, so it's minus 5. Minus 5. And so you can see that that's minus 6, minus 5, minus 11, and 1. So that's going to be 1 plus 1, A dotted with B. And we know over here from our definition of the dot product, that's our definition of the dot product, the magnitude of A times the magnitude of B times the cosine of the angle between the two. We now know what the dot product is, right? We also know what our magnitudes are of each of the two vectors. So let's just box this off down here for a second. And let's just look at that definition then. A dotted with B equals the magnitude of A times the magnitude of B times the cosine of the angle between the two. So we could say that the cosine of the angle between A and B is going to be equal to A dotted with B divided by the magnitude of A times the magnitude of B. Well, A dotted with B is equal to 1, and 7.07 times 3.74 is 26.43 approximately, something like that, 4.42 or whatever. It'd be probably closer to 2. Anyway, so that equals the cosine. Well, let's go to the next step then. What is the angle between A and B, the minimum angle between those two things in three-dimensional space? And I think that everybody can see, well, I'll tell you, 1 over 26.42, let me get that, or wait, no, it's 26, oh, 4418, I'm sorry. Let me, I got that wrong, 26.4, wow, that's not working, 4418. Got it written down here, yep. And since it's pretty close to 90 degrees, I want to get it pretty much exactly as possible. So if I take the inverse cosine of 1 over that, so 26.4418, 1 over inverse cosine gives me 87.83 degrees. So almost 90 degrees, not quite 90 degrees. When I made this example problem up, I did not make it up so it would be close to 90 degrees. It just happened that way. I just picked some numbers, you know, out of my head. Or who knows, maybe students gave those to me the first time, and they just so happened to be that, unless I had a quirky student out there that actually saw the first day and then gave me the next one 90 degrees off. I don't think so, though. I think I put those together and just pulled them out of my head, and it just so happened that it came out to be about 90 degrees. All right. Now, that is the dot product. Now, what I want to do is I want to look at the cross product. And again, like I say, I'm going sort of fast. I would maybe spend more time on this, if you weren't seniors and if you hadn't had me for engineering mechanics. And you're probably all going to say, no, we didn't have you for engineering mechanics. It was another group of students. Okay, but anyway, let's keep going because whether you've had me or you haven't had me, I want to go through this. So let's look at the identities of the cross product. What is the cross product? So A cross B, the magnitude of A cross B is going to be equal to the magnitude of A times the magnitude of B times the sine of the angle between those two. Does everybody see that? And you see why I put the absolute value signs around A cross B, because that would have to be a scalar, right? Because this is a scalar, this is a scalar, and this is a scalar. So if I multiply three numbers together that have no direction, then it has to be a number. And A cross B is not a number. A cross B is a vector. Whereas A dot B gives me a scalar, A cross B gives me a vector. So in vector arithmetic, there's two ways to multiply. There's the dot product and there's the cross product. And I'm just using the cross product here, but I want to show you what the cross product actually is. This is the definition of the cross product right there. But how would I take those vectors that I have up here, A and B, and cross multiply them? Now look at the definition again. Let's think about this for a second. Just like we looked at how these went together over here, the unit vectors. Let's look at how the unit vectors go here. Well, if I had I hat crossed with I hat, like I did up there, well, we know what the magnitude of that is. That's 1. We know what the magnitude of the other one is. That's 1. And we know what the sine of the angle between them, because they're going in the same direction, that'd be sine of 0 degrees. Well, what is the sine of 0 degrees? And I think everybody knows the sine of 0 degrees is 0. So I cross I gives us nothing. I cross I gives us nothing. But what about I cross J? Well, that's 1, right? I is 1. J is 1. And it's 90 degrees, so it'd be the sine of 90 degrees, which is 1. Does everybody see that? That equals 1. So that would give us 1. So we can do I cross J. And here's what I want to teach you, and I want you to look at. And like I say, for those of you who've had me for engineering mechanics, you've seen this before. This is not mine. This was Beer and Johnston, probably the greatest text ever for statics and dynamics. IJK. IJK, and you know, look at it, it's going backwards. That's because my right hand, if my thumb points up, look at the direction of my fingers. They're going counterclockwise, aren't they? Counterclockwise. Woohoo, baby! Counterclockwise. So there you go. So IJK. Now, if I go in the direction of the arrows, which are counterclockwise, then it's positive. I cross J equals K. J cross K equals I. K cross I equals J. If I go against that, it's negative. I cross K is minus J. K cross J is minus I. J cross I is minus K. Does everyone see that? See how that works? I'm not going to write it all out here. I would write it all out if you were freshmen, but you're not. You're seniors, so you realize what I'm saying there. What I want to do is I want to do the cross product as an example with these two vectors that we have up here. So let's just do this together. So 3i crossed with minus 2i, that would be 0, right? Because i's crossed with i's would give us 0. So 3i crossed with 3j, because I'm doing A cross B, right? A cross B, not B cross A. You're probably saying to yourself up here, hey, how about that dot product? Does that dot product commutative? Is A dot B equal to B dot A? And the answer is yes. Yes, of course it is, or I wouldn't have written that. I know it's getting late in the day. No, yes, that is true. That is not true for this. That is not true for this. In fact, what is true for this, I'll tell you right now. A cross B equals minus B cross A, right? So that's what it is. But we're not doing that now. We're doing A cross B. So then we start with A, and we just go through B. 3i cross 2i, 0. 3i cross 3j is 9k. Does everyone see that? I crossed with j gives me k. I crossed with j gives me k because I'm going in the direction counterclockwise. Okay, let's do the next one. 3i crossed with minus 1. I might as well put the 1 there. Minus 1k. Well, 3 times minus 1, that's minus 3, right? So let's put that down there. So plus minus 3. And then let's do the next one. I crossed with k. I crossed with k. Well, I'm going against the arrows, right? I crossed with k gives me minus j. So minus j hat. Let's do the next one. Well, we've run out of the 3i's, so let's do 4j. 4j crossed with minus 2i. Well, 4 crossed with 4 times minus 2 is going to give me minus 8, right? 4 crossed with minus 2 gives me minus 8, and then j crossed with I. J crossed with I, I'm going against the arrow, gives me minus k. How about the next one? Well, we've got 4j crossed with 3j. Well, that's 0. 4j crossed with minus 1k. Well, 4 times minus 1 is going to be minus 4. And then j crossed with k, let's look here. J crossed with k, I'm going in the direction of the arrows, gives me positive I hat, right? Okay, so we finished that. Now let's do the last one. 5k crossed with minus 2i. 5 times minus 2 gives me minus 10. And k crossed with I, k crossed with I, going in that direction, k crossed with I gives me positive j. And then the last one is going to be 5k crossed with 3i. 5 times 3 is 15. And then k crossed with j. K crossed with j, we're going in the opposite direction here. gives me minus I. All right, well, let's add all of these up now. So the first thing that we'd want to add up is all of the I's. You know, we could sort of, excuse me, we've only got two I's here. We've got a minus 4 times I, that's minus 4I. And then I've got a 15 times minus I, so that's minus 15I. Minus 15 minus 4 gives me minus 19 I hat. Does everyone see that? Okay, let's go on to J. So I've got minus 3 and minus J. So that gives me plus 3J, right? The minuses cancel out, so I get 3J. And then over here, I've got minus 10J. Positive 3J minus 10J gives me minus 7J hat. All right. And then let's do the last one here with the K's. I've got 9K hat minus 8K times a minus K. The minuses cancel each other out, so that makes it positive 8K plus 9K. So that gives me plus 17K hat. And there you go. So that's A cross B. If this is A, I'm going to just write this here, A cross B. And then I'm going to circle it. That's A cross B. Now, that's not what we want for that definition, though, is it? It's the magnitude of A cross B. So the magnitude of A cross B is going to be the square of each one of those taken to the square root. And so when we do that, we end up getting 26.42. 26.42, I believe, something like that. Okay, so now we go back to this definition and we say, well, the sine of theta, right? And let's hope, for our sake, that both of these come out to be the same. If you remember the last time we solved for that using the definition of the dot product, not the definition of the cross product, we ended up getting 87.83. So what would we get here? Because this is going to be the sine. So we've got A cross B, which is 26.42 divided by 26.4418, right? And that's going to be the sine of that. So if I wanted the inverse, or I take the inverse sine of that, that will give me the angle between A and B. And let me just do that just a second. 26.42 divided by 26.4418. Taken to the inverse sine gives me 87.67 degrees. And as you can see, because we've got a little calculator error in there, we're very close to the 87.83 degrees that we calculated using the definition of the dot product. So there you go, with dot product and the cross product, and this is how we use the cross product and find out all the things. And these are the definitions of all of the cross products. Oh, you know, to finish this lecture off, what I think I'm going to do is just mention a couple, just a little thing here. I'm going to just slice this off. I'm going to say, you know, what happens? We know, just talking about permittivity, we know the permittivity of a conductor is infinity. Now, how do I know that? I know because when I go from the electric field in a conductor always equals 0 volts per meter. You can't have You can't have an electric field in a conductor, can you? Because let's say, let's say that I had a conductor. I'm just going to draw this up here. Let's say that I had a conductor, and it's copper. So I got a copper conductor right here, and it's a block of copper, right? Block of copper, and I attach 5 volts here, and I attach 0 volts here. What's going to happen? And I ground this or whatever. Well, I'll tell you what's going to happen. There's not going to be any electric field in there. The electric field that you have in there is still going to be 0, right? 0 newtons per coulomb, because remember, an electric field can be newtons per coulomb or volts per meter. They're exactly the same combination of primary units. So there's not going to be 5 volts and 0 volts. There's going to be 5 volts and 5 volts, right? I mean, isn't that what we know happens? That's right. So there can be really no, if we've got nothing here and we know, and out here, let's say that we can have electric fields. Let's say this is air and this is copper, right? So out here, I've got an electric field. And so if I've got an electric field, then I can also have flux. I can have electric flux. And what is electric flux? Electric flux is just epsilon times my electric field, epsilon times E, right? So if I have an electric field out here, some finite electric field, and I multiply it by the permittivity out here, like E1 times epsilon 1, then that's got to equal, right? Because the flux here, D1, has to equal D2. The flux on one side of the surface has to equal the flux on the other side of the surface going into that surface. So if E1 times epsilon 1 has to equal the electric field in the conductor times the permittivity of the conductor, right? Then this has to be infinity, because only 0 times infinity equals anything. And this out here already is anything. This is like, let's say, an electric field of 5 volts per meter, and this thing being, so this has to be. I'll go through that in a deeper sense when we start to look at how waveforms propagate through different media. That's much later in the course, but I just wanted to point that out to you as one thing toward the end of the lecture. But the truth is that every waveform does penetrate a conductor, right? The truth is always stranger than the theory. The theory says, no, there's never going to be any waveform that penetrates a conductor. Not true. In fact, this equation I'm giving you right now is called the skin depth equation. The skin depth equation, or the conductor penetration equation, how far an electromagnetic wave will penetrate into a conductor, and it's pi times the frequency of the wave that's impinging on the conductor times the permeability of the conductor. That's why I put that C there. Now, that C still means, I mean, we're still talking about the permeability of the conductor equals the relative permeability of the conductor times the absolute permeability. Let's not forget that. But this, right, this is the permeability of the conductor times the conductivity of the conductor. And in our next lecture, I will talk a little bit about that and how it pertains to seawater. Maybe it won't be my next lecture. Maybe it'll go for a little while, because my next lecture, actually, I've got something else. But we'll be talking about that, because seawater is conductive, right? And how in the world do we communicate with, I should have written this over here, mu sub C equals mu sub R sub C times mu sub O. And of course, I didn't. Let's not forget that mu sub O equals 4 pi times 10 to the minus 7 henries per meter. And I don't want this video to go too long, so I'm going to cut it off right there. Okay.